Hello everyone, I am Deep from IIT Delhi. I am your math faculty for class 12 NCERT Mathematics. If you want to score good in class 12 Mathematics, you are at right place. Here we are going to do each chapter one by one and we are going to cover whole NCERT. So let's start with chapter 1. Hello. So today we are going to do class 12 chapter 1 relations and functions introduction. So in this introduction we are going to cover the content of chapter 1 relations and functions. In this which topics we are going to cover are relation and function, then composition of function and invertible function. So let's move forward. Okay. So let's first recall definition of relation. What is relation? Relation. So relation, in relation there are involved two. First of all, there needed two sets x and y. X and y be two sets. Then relation R is subset of Cartesian product of x cross y. Let me give you one simple example. Suppose we are having set x as a comma b comma a comma d comma y, and take y as some name randomly, say Nisa, Deep, and yes. So now I am going to define relation on this Cartesian product x cross y. I will define relation as pairs xy such that x is first letter of name y. Right? Did you got this right? What it is saying? That it will contain then what elements? First, if I take A, then is there any name in Y whose first letter is A? Yeah, so it is Anisa. Similarly, D, Deep, and Y, yes. So this R is subset of Cartesian product x cross y is called relation. So let's move ahead. Now there are 6 type of relations: empty relation, universal relation, reflexive relation, symmetric relation, transitive relation, and equivalence relation. We will do definition of each relation one by one. So what is first empty relation? Empty relation. If we are defining R subset of some set, say x cross x, and we find that if R is empty, that is set R is empty, then we'll say R is empty relation. Then R is empty relation. Right? Let's take one simple example. Take x as 3, 4, 5 and R as element of x cross x such that x is multiple of y. This xy belongs to x cross x, okay, such that x is multiple of y. Here neither 3 is any multiple of 4 5, neither 4 is multiple of 3 5, or nor 5 is multiple of 3 5. So R is empty, hence R is empty relation. Now next is universal relation. If we are getting R as whole set, whole Cartesian product x cross x, then R is universal relation. Then next was reflexive relation. What is reflexive relation? Reflexive relation if for every x belongs to x, x comma x belongs to r, then r is reflexive relation. That is, if you are defining any relation R and you are picking any element from X, then you should find corresponding X comma X pair in R. Then relation is called reflexive relation, and this X comma X belongs to R should hold for every X in X, capital X. Then what is symmetric relation? Symmetric relation. That is, R is symmetric relation if you are finding x comma y in R, then you should also have y comma x should be in R. If this hold for every xy in R, this is not script R, this is R. Yeah. So if this hold for every x comma y in R, that is, if you are having x comma y in R and you are able to find y comma x in R, this hold for, if this hold for every x comma y in R, then relation is called symmetric relation. Then next was transitive relation. That is, if you are finding xy, if you are taking two element xy in R and another is yz in R, if you are able to find two element like this, that is x comma y in R, then y comma z in R, then if you are able to find x comma z in R, and if this hold for every such type of element, that is, in what way I am trying to say is that if you are able to find, if you are finding that xy is in R, then you are also able to find that yz is also in R, then you should have x comma z in R. If this hold for every such elements in R, then such relation is called transitive relation. I will give example having reflexive, symmetric or transitive property. Before that, what is equivalence relation? Equivalence relation is R is equivalent, sorry, R is equivalent relation if R is reflexive, R is reflexive, symmetric, and R is transitive. Then R is called equivalence relation. Now let me give one simple example. Suppose if I am taking x as set of integers, x as set of integers, and I am defining R as having element x comma y such that x is equals to y, and this x comma y, x and y are from integers. So I am telling this R is reflexive, symmetric and transitive. First let's show reflexive. Why it is reflexive? Because for reflexive, what you want, that whatever x you take from integer, x comma x should be in R. And for x comma x to be in R, what condition you need to be hold, that for that x should be equals to x, right? And this hold, right, as x is equals to x, which implies that x comma x belongs to R. Hence this R is reflexive. Now why it is symmetric? Suppose you are taking x comma y in R, what it will give, that x is equals to y, right? But this also means that y equals to x, as both are integer, and y equals to x will give you that y comma x is in R, right? Similarly, you will be able to find transitive. Why so? I will show transitive in next page. So why it is transitive? Suppose x, y and yz is in R. What does this mean? That x is equals to y and y is equals to z. Does this implies that x is equals to z? right? Because x is equals to y and y is equals to z. Because y equals to y, it will imply x equals to z, and this will give x comma z is in R. So this will imply R is transitive. So we got R is reflexive, symmetric. R is reflexive, symmetric, and transitive, which will imply R is equivalence relation. Right. So we got R is to be equivalence relation. This we did, right. Now what is next is we got the definition of equivalence relation, right. Next is equivalent class. What is equivalent class? Equivalent class of any element A belongs to X will be given as equivalence relation, equivalence class of A containing A belongs to X for an equivalence relation R in X is the subset of X containing all element B related to A. Okay, let me write it in mathematical way so you will get it more. So what is class of A where A belongs to capital X? It is defined as all B in X. First of all, R is relation of X cross R, relation over set X. So what is class of A? Class of A will contain all B belongs to X such that A comma B belongs to R. That is, B is related with A. Right? All such B such that B is related to A. This is called equivalence class. So if I write the relation which we took equals to an integer, that is two elements are related if they are equal. In this, what will be equivalence class of 2? It will contain all B belongs to that X was our integer. So all B belongs to integer such that B is equals to 2, because we had defined relation as equals to. So how many elements will be equals to 2? Only one, which is singleton 2. Right. So class of 2, equivalence class of 2 will contain only one element 2. Note that we can talk about class when it is equivalence relation. That is, we always talk about equivalence class. We don't talk about only general class. Okay. There is one more relation, example of equivalence relation, parallel to between lines. That is, two lines are related. I am defining relation as this is called sign of definition. I am defining relation as two lines are related if they are parallel. It is your homework to verify that this relation is equivalence relation or parallel. Okay, now let's move forward. So what next is, now let's move to function, right? So now let's do functions. I think you know the definition of function, still just recall it. A function is a relation from set A to set B such that every element of A has one and only one image in B. So function is one type of relation, okay? From function is a relation, that is function is subset of X cross Y. Okay, here we are taking set to two sets as A and B. So function is subset of A cross B. So how function is defined, that we denote function like this, that is f is function from A to B. So it should have property that whatever you have to take every element from A, that is A is called domain. This is domain and this is codomain. So for every element in A, you should have only one image in B. Only one image in B. And this type of relation is called function. Okay, so let's move forward. Now there are different I am not giving in detail about function because it is covered already in class 11. So now next is what are type of functions. One functions. When is function is called one function. Suppose I am taking function from x to y. When function is called one function, that is f is from x to y, right? So let me first I will show everything by diagrammatically, every definition by diagrammatically. So if I am taking some function from x to y, when it is called one function, if every every element uh, sorry, every pre-image of element in Y should contain only one element. That is, in what sense I am trying to say that if I am let me first plot some function like this. Yeah. So every element have only one pre-image. Suppose I am taking this element. So these have only one pre-image, right? It don't not two elements are floating in this same point, right? So this is called one definition. That is, every every point should have different images. Okay. So next is onto function. What is onto function? I think this is misprint. There is no into function. There is onto function. So what is onto function? Onto function when when every element of y when every element of y have pre-image in x, then such type of function is called onto function. Like there should not be any element remaining in y which don't have pre-images. So this is example of onto function because every element in y will have pre-image. But if you look it into this example, this is not onto because this does not have pre-image. Does not have pre-image. So that is not onto, but this is onto, right? So you got what is one, you got what is onto. Now what is bijective? Bijective. If sorry, bijective function. So f is called bijective if f is one and onto. Then it is called bijective function. So you got what is one, you got what is onto, and you got what is bijective. Now let's do how to find that whether function is one and onto or not, because you can't always plot it like this diagrammatically and see whether that every image have pre-image, so it is onto, and to see whether only one element is being plotted to any element in y or more than one element are being plotted to any element in y. This is not always possible, right? So there is method to check whether function is one or not. So first of all, let's see when we can say function is one or not. So what you have to do, is you have to take any x1 x2 randomly from x, that is codomain, sorry, domain, and you have to take, suppose f of x1 is equals to f of x2. What does this mean? That f of x1 is equals to f of x2. That is, x1 and x2 are such that their image is same. That is, that image in y, and that is f of x1 equals to f of x2. Its sum equals to, say, y belongs to capital Y. So there is only one element, y belongs to y. Now for function to be one, what should we have? That this x1 should be equals to x2. Why I am saying like this? Because if x1 is not equals to x2, then what you are having, that x1 is not equals to x2. Suppose suppose x1 is not equals to x2, but you are having f of x1 is equals to f of x2. So what this will give, that two different elements have same image. So this will contradict that our function is 1 1. So for function to be 1 1, we should have for always for all the element having this property that f of x1 is equals to f of x2, then we should have x1 equals to x2. Then only we can say that function is 1 1. So you got it right, how to find that whether function is 1 1 and 1 1 or not. So for that you have to take some arbitrary element, two arbitrary element from x, then you have to say that let f of x1 equals to f of x2, and if you are able to prove that x1 is equals to x2, then our function f will be 1 1. So you got it, how to show 1 1. Now let's see how we'll show f is onto or not. So for that you have to pick random arbitrary element from y. That is, you have to pick any element from y, and for every element in y you should be able to find element from x. That is, there exists some element in x whose image is y. Why this will give onto? Why this will give onto? Because just see, let me show it here. If you are picking any arbitrary element from y, say this element, and if you are able to find x in x such that our f of x is y, which we had picked, then our function is onto. But this should hold for every element we are picking from y, not only one element. Here we have taken this element, then we have to take this element. For that also we should find its pre-image. That is, we should find some x belongs to x such that its f of x should be this. Then again we will pick another element. In this way we will have to pick every element from y and to check whether that elements have pre-image or not. Okay, so this is how we will find whether function is onto or not. Now what is bijective? How we'll find that the function is bijective or not? So you should check that whether it is 1 1, and then check onto. If you are getting 1 1 and onto both, will give that function is bijective, right? You got it right, how to see whether functions are 1 1 and onto. Now let's move to next topic, composition of functions. So suppose we are having two functions, first f from x to y, and then y, sorry not y, then g from y to say some x only. It can be not necessarily it should be x, it can be, suppose rather than x let me write h, y from h. Then we will have we will have we will have composition of function defined as g of f. How it is defined? It is defined from y to, not y to, sorry, x to h. How it is defined? G of f of x is defined as g of f of x. What does this mean? Let me show you by graphically. Suppose this is your x, right, and then this is your y, and this is your h. So what is g of f of some random element x? I am taking this element x. So you should first put it in f function. You will find f of x. Then on that f of x, it is acted by h. then you will get h of f of x. You got it right? How it is? Sorry, not x. This function was g. It is acted by g. Then you will get g of f of x. So what is g of f of x is g of f of x. You got it right? How composition of function is defined. Next is invertible function. Okay, first note that you can also for defining g of f, you should have domain of g and codomain of f should be equal. That is, codomain of f should be equals to domain of g. So similarly, if you want to define f of g, what you should have? You should have codomain of g should be equals to domain of f. Right? Right, like f, g of f, we can also define f of g. But condition is that it should have codomain of g should be same as domain of f. Now let's move to next topic, invertible function. The function f from x to y is said to be invertible. Is invertible if you are able to find some function g from y to x such that f of g, you should get it as what will be domain of f of g? It will be y, right? First g will act, so its domain should be y, and its codomain will be g will act from y to x, then f will act on that from x to y, so its codomain will be finally y. So you should have f of g as identity, but this identity I will denote it by y. I will tell you why I am denoting it like that. And similarly, you should have g of f should be say identity function, and here I am denoting it as x. Why I am denoting it as x and y? Because this I will have, this I is same as f of g, right? And f of g is function from y to y. So this y, this identity is having domain and codomain as y. So I am denoting it as iy. Similarly, ix is g of f. It's from x to x. So function is called invertible if you are able to find g such that f of g is same as iy and g of f is same as ix. Let me give you one simple example. That suppose you are taking f from x to x, my x and y both are same, defined as f of x is x. This is identity function, right? Now I am saying that this function is invertible, so for that I should find one g such that f of g should be same as g of f of g should be identity and g of f should also be identity. So let me define g as identity function, right? So what will be my g of f? Now this is your homework to verify that g of f you will get it as identity and f of g you will also get it as identity. So we got that our f is invertible. You should verify, right? This g of f is f of g are identity. Why now I am not writing here x and here x separately? Why? Because my domain and codomain both are same. Okay, so this was chapter 1 introduction part.